Howdy! We're going to continue on with Chapter 14, Systems Hardening and Baselines. This is our third or fourth videos, and we're going to be talking about host-based security controls, talking about what goes on at the machine for the express purpose of providing data protection on the host. Okay, you can read the slide as well as I can. What does this mean? Okay, what are we going to put on the machine that's going to provide access control? Data protection is all about access control. So we can do this in a number of ways. We can do encryption devices. So we can have an encryption device. The good thing about a hardware-based encryption device, if there's no software involved in it, it does some kind of hardware function, then the only way to bypass that encryption is through a physical attack because it's hardware-based. It's designed to assist in the encryption decryption activities or actions, hardware rather than software. So it provides another level of protection. The problem with the hardware device is if you were doing it on a computer, you're going to have to put one on each computer. But it does give you an extra level of protection that there has to be a physical breach to get to the hardware encryption. So we're going to go through this part quickly. We're going to talk about the Trusted Platform Module. It's a hardware solution on a motherboard that assists with key generation and storage. So when we talk about key generation, go back to the chapter we had on PKI. So they're stored in that Trusted Platform Module. They're not accessible via normal software channels. Because of this, they're physically separated from the hard drive or other encrypted data locations. Again, any attack against them is going to have to be physical. Meaning you're going to have to get to that hardware. So hard drives offering encryption services can provide flexibility in terms of performance and security. So you can buy hard drives today that have encryption built into them and very good encryption algorithms such as AES. And again, it offers significant performance and security solutions because if it's in the hardware, it's going to be faster than if it's software layered on that. Data encryption is the best solution. If it's properly encrypted, the data is not readable. And there's a lot of ways to enact this. And a lot of them is being done, and you are not even aware that maybe it's going on in your machine because it's part of your operating system or part of the equipment that you have implemented. So for some high-performance data stores, the performance is critical. You can achieve better performance through specialized hardware. You have to see also what these machines are being used for. Is the overhead in that level of full disk encryption worth it? I've worked on systems where we had full disk encryption, where we had logins, where we had all this other stuff going on. It gets rather cumbersome. And then you would encrypt individual files within a system. This was a cybersecurity company I was working with, so I guess I wanted to practice what they preached. However, it almost went to a little extreme. So you have to remember that a performance hit by full disk encryption could be critical to the operations. In an industrial control system environment, in a non-IT environment, in the OT environment, operational technology environment, you may not want to do this because the performance cost overhead may hinder operations to the point that the performance degradation is not acceptable. So when we talk about data security, we're talking about the most important element to protect on the enterprise. Earlier in this semester, we talked about how trends and evolution had occurred in cybersecurity. At one point, we were worried about machines. Now we talk about information assurance. Our focus is on protecting the information and the data. So, if equipment's compromised, it can be replaced. But if information is stolen, it's going to be a critical asset of an enterprise, of a nation. So it's a different animal than if you worry about the equipment. You can, in Shamoon attack in Saudi Arabia, the story was 30,000 machines were compromised. They could not be cleaned. They basically took them out of the desert, a few well-placed flamethrowers, and destroyed the machines. But the value of the information, the fact that their operations were shut down for about 2 weeks at the cost of millions of dollars a day to the kingdom, that's the problem. That's the issue. So we talk a lot about network security and host security, but let's focus on what we're really talking about. We're protecting the data. So how do we take that to secure the data wherever it resides? And again, go back to my womb to tomb, from creation to transport to processing to storage to destruction. So data in transit must be protected, and we talk a lot about that data in transit being protected when we talk about network security, moving it from one system to another. And our typical method is encryption. But the fact is, we need to look at the entire life cycle of that data. Again, data in transit, going across the network, going across the internet, we tend to focus on this. But what about when it's at rest, when it's at the machine, when it's archived data? So the last point here is very important. What is important to ensure that data is always protected in proportion to the degree of risk associated with a data security failure. If I were teaching you risk assessment, we start with how do we categorize the criticality of our data. And I don't do it quantitatively, I do it qualitatively. Low, medium, high, meaning perhaps where I teach in the fall is an open schedule, where my classroom is, that's low criticality data. But high criticality data would be the grades I give you in that class. Medium criticality data may be something in between, maybe data that needs to be known only to Texas A&M students, not to the general public, but is still for general distribution. So low, medium, high. Data in transit must be protected, but I want to emphasize again, womb to tomb, from creation through processing, storage, transmitting, into destruction. So data at rest must be protected. I guess I've kind of already hit this. Whether if the media is stored, data at rest still requires protection. What do we mean by data in rest? Is it on a database? Where is it? Is it on a USB now because someone took it on a USB? Is it on backups? It's not being transmitted. It's, quote, sitting somewhere. It's in a database. Where does that data exist? Do we have the level of data protection commensurate with the risk? So data in use, same thing. If it's processed in an application, it can be in risk when it's at system memory or even in the active processing. It may not be in transit from machine to machine. It may be resident in memory. So again, we need to look at the totality of protecting memory schemes, the address space layout, secure coding, all of this. So what I want you to get out of this is the womb to tomb and the special problems each presents. So when we talk about data being in process or in use, it's in memory. So can it be accessed when it's in system memory? And big data, as I love this term, we've always had big data. The problem or the issue is, and I think that term may be becoming passé, we've always had voluminous data, volumes and volumes and volumes of data. All this data around, we didn't have to process it. We talk about big data now because now we have the hardware, software, and quite frankly, the mathematics behind the algorithms to be able to process huge amounts of data. But planning for security when you're handling data is enterprise level thinking. Because that data is, first of all, going to be a lot of data that may be personal data. You may have low criticality data, medium criticality data, but once you put in high criticality data, everything goes to the extremes. So first of all, you have to worry about the security level of the data. Then you have to worry about where all that data resides, where it sits, where it's being pulled from, where it's in transit. So it really complicates this scheme. Cloud storage is another. I don't know if we'll talk about it in this class. I probably should add a module. If not, if you are interested in cloud security, look up FedRAMP, FedRAMP. FedRAMP is the federal guidelines for securing cloud data. If you're really interested in it, go to AWS, Amazon Web Services. If you look through their certifications, you will find out they are FedRAMP compliant. It's a great scheme for compliance. Unfortunately, the regulations only extend to cloud storage. Any data that's being held that is government related has to be FedRAMP compliant, which is why AWS and these other large cloud service providers do the FedRAMP. I hate to do a plug, but my risk assessment, risk management class, we talk about FedRAMP because it is very important in this. And it defines the encryption, it defines the processes, how things are done to the extreme. Very good, which we don't have the same thing. If I've got the data on a host and I'm not pushing it to the cloud, I don't have to, I've got different requirements, much lesser standards. Access control list, they're one foundational issues for security on anything, not just the machine. Who can get into my facility? That's a physical. What you're allowed to bring in. Your access control list, what you're allowed on, which computers you're allowed on, what you can do on those computers. ACLs and permission are basically access control, which is the basis of all good cybersecurity. So whether we talk about it using by the operating system or level of permissions for accessing applications, or how you're going to, our users going to manipulate, use, or edit or delete data, access control lists are pervasive through computer security. Now we talk about network hardening, and it's putting the controls over the network access. And these network devices should be configured with very strict parameters to maintain network security. One of the things that you need to read in the OPM paper is the lack of adhering to good basic cyber hygiene on their logs. So when we talk about network hardening, we not only want to put into place all the controls to control the services that are running, the ports that are open, the network devices you can hook in, the operating systems, and what level you must have, what version if you're doing your patching, but we also want to go back and audit that by looking at our log data. I have a very basic paradigm about security. For instance, with training, effective training is only done through auditing. You can think of it like this class. I give you information and I audit to see how well you've learned that information through assignments, midterms, exams, and the like. Well, the same thing. If you're doing the network hardening and you think it works, you want to verify that checking your log data to see if there's anomalies that would say, hey, ports are open that shouldn't be there, services are running that shouldn't be running, network devices are being attached, data exfiltration is high, there's something wrong. We got to go back and harden the network. And of course, software updates again. It's like I said earlier, if you do your patches, it's one of the most important things you can do to maintain security. Now we're going to talk about device configuration, and I could go on and on about this. It's really hard in a complex enterprise to keep your devices all properly configured just because of the dynamic nature. But when we talk about this, we talk about patches, we talk about good passwords and the like, but you also have to figure out which devices are running just with any computer. You need to limit access to those who need it. You need to choose good passwords. You need to password protect console and remote access. You need to turn off all unnecessary services. You have to do all this. Proper configuration is important to these. And when you think about the fact that you have a number of computers, then you have routers, switches, you have all this complexity, then you have to figure that each device must be configured correctly. So again, you want to limit access to those who need it. You want to choose good passwords. You want to password protect your console and remote access. You want to turn off unnecessary services. You want to do these kind of things to make sure that your device is configured securely. And security management interfaces. Some network security devices have management interfaces that allow for remote management. Oh, great. That's so nice to be up, in Montana and you can remotely manage your devices themselves, but it provides complexity and complications. So you'll see it a lot on firewalls, routers, switches, management interface that allows all this. But due to this high level of access, you need to be sure that these these management interfaces and applications are secured against unauthorized access. Should be connected to public network connections, DMZ connections, When possible, this access to the management interface and applications itself should be so highly restricted with an organization to ensure that employees with the proper access right and privileges need to be the ones to connect to these. And those that lack those proper access rights and privileges cannot connect to this. And then we have application hardening. So you harden applications, do the same thing. You remove the functions or components you don't need. You restrict access where you can. You make sure it's up to date with patches. And with application, different version control and the like, you have to be sure that this gets done each time. Does a new version give you a function or component you don't need? And as with operating systems, applications have recommended security and functionality settings. So in some cases, vendors provide recommended, or you have an industry that provides it. But most large organizations, and this is true, this last point, develop their own application configuration baseline so that they is customized for their particular enterprise. So developing this and using it anytime the application is deployed within the organization helps to ensure a consistent, and hopefully consistent means secure configuration across the organization. We're going to close with this on application patches. They're likely to come in three varieties, as I talked about: hot fixes, patches, upgrades. Remember, hot fixes usually targeted on one software application. Many times a hot fix means we got a problem, we got to fix it. Patches are a little more controlled. We have a set of hot fixes and bug fixes and other things we have in there. And then upgrades are where we've added functionality in a more controlled manner itself. So again, hot fixes are usually small sections of code designed to fix a specific problem. For instance, let's say there's a buffer overflow and the login routine for an application. Patches are usually collections of these fixes, tend to be larger. They're usually released on a periodic basis or whenever problems have been addressed to warrant a patch release. Upgrades are, again, maybe patching, but perhaps patching of low risk vulnerabilities. The upgrade term is like, oh, there's nothing bad going on. This is just an upgrade to your system. But basically, you just want to remember the differences between the three: hot fix, patches, and upgrades. And, many times upgrades consist a lot of fixes rather than new or enhanced functionality. As I alluded to before, I was in the business at one time of developing software, releasing software, and supporting customer bases with software. And we would do upgrades twice a year. We're going to get upgrades. Maybe there's just little bugs being fixed. Maybe we've actually added functionality. That all depends on your business model. That's the end of chapter 14, video 3. We will end now with chapter 14, video 4. Stay with me. Thank you.